In honor of the greatest student ever, Beauregard Lomsterfling, ding ding bingling. Okay, so what we're talking about here are, for nuclear reactions, we're going to be talking about Q values, or for something like an alpha decay, what can be considered a disintegration energy. Essentially, when these reactions occur, alpha decays, beta decays, or gamma decays, we can have some releases of energy here. And as a result, it would be nice to know how much energy could kind of be released, or does that reaction even want to happen? So the way we take a look at this is we take a look at two sides of our equation here. Let's take a look at an alpha decay. For an alpha decay, we had N with Z and A, and it yielded for us some new element, M prime, of some Z minus 2 and A minus 4 plus an alpha particle, which we know as helium. So there's our helium-2,4. We like to call everything on the left side, what we started with, these are the parents. At the moment, we only have one, but in nuclear equations, we could have a neutron over there, and that could be a part of our parent system as well. On the right side of our equation, everything else we get here, we call these the daughters. Why? I don't know, but it's what we do. Now, what we can say from this is, if we take a look at masses, and this kind of starts getting back into the idea of binding energies, although slightly different. If we take a look at the masses of our parents and the daughters, then we can relate the idea that mass is energy. We know that mc squared equals E. Thanks, Einstein. So what we can start saying here is that if we take a look at masses of the parents and masses of the daughters, what can we do with our energy? Well, if we say that the mass of the parent times c squared, this in general should be greater than the mass of all of the daughters. And in our case here, this would be like the mass of the daughter particle, which is, the new thing we've got. So we'll call this md, c squared. And then plus this helium here, while we can kind of think of it as being like in the term of the daughters, we actually know it as an alpha particle. So this should be the mass of an alpha particle, c squared. We might also get out of this some extra Q value. And from thermodynamics, we know this Q as just being energy. So through this alpha decay, we could get these daughter particles out, but we can also get some energy out of that. Now, looking at this equation here, we could then solve for Q. If we solved for Q, we could say that Q, or this Q value, this would be equal to the mass of the parent times the speed of light squared, minus, and then this will be the mass of the daughter, c squared, plus the mass of that alpha particle, c squared. If we wanted, we could just put minus and then minus for each of these. Yes, the minus is distributed. Yes, technically you could pull the c squared out of all of these because the c squared's everywhere, yada, yada, yada. But however you write this out, we have what we initially have minus what we had at the end, the parents minus the daughters. And doing this gives us a value of Q. It gives us a Q value. For these alpha decays, we call this a disintegration energy. And this Q value effectively measures efficiency. It measures the efficiency of your reaction. In general, if the mass of the parent is less than the mass of the daughter plus, whatever else comes up, like this alpha value, then in that case, what you're going to have, or what you will be able to say, is that Q is going to be less than 0. If Q is less than 0, then this reaction could not occur. This reaction couldn't occur because you simply didn't have enough energy. If we have to conserve mass and mass energy, then where are you just pulling this magic mass, this magic energy out of? Like, bloop, it just can't come out of thin air. That's not possible. So the mass of the parent, in order for something to occur, should be greater than that of the daughter and any other particles that are created. Now, it could be a case where we have a parent and some energy added in that could cause some reaction to occur, but just a stationary particle doing nothing, in that case, this is what we'll see here. While we use this specific setup for alpha decays often, we have a slightly different setup, which is really just this rewritten, but we look in terms of kinetic energies. If we think about this from a kinetic energy standpoint, then once again, we know that the mass we had initially, those parents, have to be greater than the mass we have at the end, at the final, for those daughter particles. So if we're just conserving energy, then another way to kind of write this, if we have more than a particle, is let's say we've got two things initially. We've got A and X. These particles will yield Y and B. Now, in this case here, we're still going to find a Q value, but this time we tend to call it a reaction energy, because this right here tends to be used more for nuclear reactions. We're not just talking about alpha or beta decays. We're normally talking about a nuclear reaction here. Normally one of these is going to be a neutron in some way, and we'll see that in a later video. But for these type of setups, it's a very similar idea. What we're going to have is, once again, our Q factor, our Q value here. This is going to equal the mass of A plus, I don't know why I used a capital M there, that's a little weird. Mass of A plus the mass of X minus the mass of Y minus the mass of B times C squared. This is really just the same idea we had before. These here, A and X, these are our parents, and then we subtract the daughters. It's the same general idea. However, if we think about this in terms of kinetic energy, then things change slightly. In a nuclear reaction, what can often happen here is this particle X could be sitting stationary, and some particle, like a neutron, which could be A, could strike it. As a result, we could get two particles with some kinetic energies. Because of this, we're going to write this Q factor in terms of final minus initial, or a delta K, a delta kinetic energy. So this will look very similar, but a little different. Our Q, because it's going to be a change in kinetic energy, or a final minus initial, this is going to equal for us the kinetic energy of particle B plus the kinetic energy of particle Y minus the kinetic energy of particle A minus the kinetic energy of particle X. And oftentimes, when we do this for our nuclear reactions, that particle X was initially at rest, which means its kinetic energy is initially 0. And this can often wipe itself out of the equation. Because of this, what we see for these nuclear reactions is that if Q is greater than 0, what this means is that energy has been released. So energy has been released. We would call this an exothermic reaction. On the flip side, if Q is less than 0, then energy is needed to even get that reaction to occur. The reaction will not happen spontaneously. You need some extra energy to be put into that for it to occur. We call this one a endothermic reaction. okay? So these really just tell us if a reaction will take place, if it will not take place, what kind of energies you need to do that, maybe what kind of energies you're going to get out of that depending on the reaction. For both a nuclear stance, which is, we've kind of looked in terms of energies here more than masses, although potato, potato. Or we could do this for a disintegration energy or a Q value for something like an alpha particle, okay? But that's what we have here. We're going to move a little bit deeper into these ideas and actually start looking at some nuclear reactions for fission and fusion in a moment. This is just a nice little primer to start thinking about energies that we might have. But until next time, this is finished. Adios, and take it easy.